Cooling systems. In this presentation, we're going to be looking at system capacity measurement. How do we measure cooling? We're going to look at a larger absorption cooling system, its concept of operation and components. Then we're going to focus our efforts on compressive cooling, the concept, their components, control, and finally, we're going to finish with a look at heat pumps. Cooling capacity is measured in tons. A ton of cooling capacity is the amount of cooling that would be provided by melting a ton of ice in 24 hours. An air conditioning system that is rated at 2 tons would provide the same cooling as melting 2 tons of ice. The other method that it is sometimes measured in is BTU per hour. And this relates to the amount of British thermal units of heat energy that could be removed from the area per hour with the unit. There are two basic forms of modern cooling: absorption, which is an ammonia-based system, and compression, which is an evaporative type system. We're going to focus on absorption first. Absorption cooling uses heat as the input energy, which is a bit counterintuitive. And ammonia, which is highly poisonous and has led to significant deaths in the past. So where is absorption cooling used? Well, we use it in RV propane refrigeration. And as you can see from this diagram, which you do not have to memorize, heat is applied to an ammonia solution, which boils and then separates. The two values separating are water and ammonia gas. The ammonia gas, when it is heated and in a gas form, then flows through a cooling section, which removes the heat from the ammonia. In here, at this point, the ammonia gas is extremely cold because it has gone through this evaporative section or an area where the heat energy has been removed. It combines with hydrogen, and being extremely cold, it picks up or attracts BTUs of heat energy from within this, being the wall of a refrigerator, inside a refrigerator. It then comes back to a separator type of chamber. And again, the hydrogen dissolves out, evaporates out of the mixture, and we're left with an ammonia water solution. What's important from this is that heat is applied and that ammonia is the prime chemical that's utilized in order to accomplish this cooling system. It is most commonly used outside of the RV industry in industrial applications, where we need massive amounts of heating or cooling. Institutions, where we have multi-building campuses that require cooling, large office buildings, and also hockey rinks. It can't be stressed enough that when working with an ammonia cooling system, you must be hyper aware of the danger that it possesses. A small leak is enough to kill many people, as what happened in Fernie in 2017. What an ammonia system is made up of is primarily a large boiler, which provides hot water. A large boiler in an institutional setting could look something like this. Now, the boiler provides significant heat, and that heat is then applied to the chiller. And the chiller is the object that has the ammonia mixture solution in it. The chiller looks like this, and it's going to cause a significant reduction in heat of the ammonia solution. Now, there are two different types of air handling units that are going to connect here. Remember, the main purpose of having the chiller system is to provide chilled water. And that chilled water is then utilized in order to provide cooling for other buildings. So what's slightly different from RVs is that the ammonia solution never leaves the chiller. Instead, we use a heat exchanger. And water inside this separate heat exchanger is chilled by that interaction with the ammonia solution. Now, there needs to be a way for us to remove heat from the air inside the buildings and add heat to the rooms inside the buildings. And in these situations, we use air handling units. We have the really cold chilled water that can flow through this heat exchanger. And during winter, we use the boiler to push hot water through a separate heat exchanger. This way, we have hot or cold control in every location of the building. Now, in order for the system to function properly, what we need is a way to get rid of the BTUs of heat energy that our air handling units will pick up from the buildings. Cold water goes in and slightly warmed water comes out. And so, how do we get rid of that heat? Well, through the ammonia system and lots of different chemical reactions and heat exchangers to different areas, what ends up happening is we transfer the BTUs of heat energy to an external water supply that goes all the way out to something called a cooling tower. A cooling tower is exactly what you would think it is. It's something that cools water by exposing it to the air, and it usually has a very large fan. These are some examples of cooling towers. Again, there's no ammonia in this water. This is simply a means of removing heat from the water that was originally transferred into the chilled water that was generated by the chiller itself. Another means of looking at this would be the cooling tower on the top of the building getting rid of excess heat and that water coming back down to the chiller, and then a separate circuit of water going out to the air handling units. As the slightly warmed water comes back to the chiller, we see that it is transferred to this uh, secondary water system, and the BTUs of heat energy are then dropped essentially outside through the cooling tower. That's in a very large industrial and institutional setting. When we're working with other types of cooling and refrigeration, we are typically working with a compression or evaporative cooling system, which uses mechanical energy in order to create the cooling. So where is compression cooling used? Well, anywhere a smaller cooling value is required than what we see in absorption. Residential AC units, heat pumps, walk-in freezers for restaurants, walk-in coolers for liquor stores, food coolers in grocery stores, small industrial, small commercial. And what it utilizes is mechanical energy in the form of a compressor. Often you'll see items like this outside of homes, or this inside a walk-in cooler of a restaurant. This is more of a commercial or industrial style or size of evaporative or mechanical cooling unit. And this is much larger. Finally, we have the lowly hang out the window air conditioner, which again uses mechanical input energy. The basic concept of this system is that when we allow a very high pressure gas to escape to a low pressure atmosphere, the energy that it possesses in the pressure is released through a temperature drop. And so what will happen is we get a buildup of very cold air or gas that comes out. And this pressure drop and the appreciable difference in temperature is what we're going to use to our advantage when we are working with a mechanical evaporative style AC system. In order to sort of evaluate and look at the cooling cycle, it's easiest to simply take out a sheet of blank paper and sketch down the following diagram. We have four divided sections, two gas, one vapor, and a liquid. And what we're going to do is then place a component into each line. A compressor is an item that compresses a gas, and the gas that the compressor is compressing is called a refrigerant. The compressor has a high pressure side, and after it compresses that refrigerant gas, it comes out very hot and at a high PSI. It then goes to a heat exchanger, and the heat exchanger is called in the refrigeration world, a condenser. And the reason it's called this is because the gas, when it is cooled, turns into a liquid, and that change of state from gas to liquid is condensation. So it condenses to a high pressure liquid. Now the liquid is slightly warm, which is okay. It's still at an extremely high pressure. And what we're going to do now is we are going to drop the pressure in a very regulated fashion. And we know that when we drop the pressure, by allowing it to release into a lower pressure atmosphere, that's going to create an extreme drop in temperature. The refrigerant is now extremely cold. And what we're going to do now is we're going to pass it through another heat exchanger. This heat exchanger is called an evaporator. And that's because this extremely cold vapor is going to pick up BTUs of heat energy that are in the room that we want to cool. And in doing that, picking up the heat energy, it will evaporate. Evaporation, evaporator. At this point, it's now a cool, low pressure gas. And it goes into the compressor to be recompressed up to a high pressure, and the cycle continues. Now, it's important to keep in mind that at no point is the refrigerant gas, liquid, or vapor exposed to the air that we breathe in a building. It is a completely self-contained circuit. And it's one that we can see here with the lines. High pressure into condenser. This would be located outside, and we have a fan to blow air across it because we are essentially getting rid of or removing hot BTU energy. We then have this line that goes to a form of a valve that allows for a pressure drop. Again, this goes into an evaporator. The evaporator is in the location that we want to cool, and there would again be a fan that blows air across it. We then go all the way back to the compressor. So let's start with the compressor. A compressor looks like this, compresses the refrigerant gas. Its output is a very hot, high PSI vapor, and its input is kind of a warm, low pressure vapor. There are two classes of refrigerant compressors, hermetically sealed and semi-hermetically sealed. Hermetically sealed look more like a welded shut capsule. They're 100% sealed, and there is nothing that can be maintained inside them. If it fails, it's replaced. Semi-hermetic are types of compressors that can be maintained to a certain fashion to a certain degree, and they're seen on the left, whereas hermetically sealed, an example is shown on the right. Hermetically sealed motor compressors have a section in section 28 that discusses their operation and sizing requirements. What's important to realize is that this type of motor is mechanically connected by a crankshaft to the piston that is creating the compression of the refrigerant itself. The type of refrigerant that is utilized actually flows around the motor itself, and there is a small quantity of oil in the bottom to ensure that the connecting rod is adequately lubricated. This is what it would look like if removed from a deep freeze type of freezer in a house. And if we crack it open, it sort of looks like a pump, and it sort of looks like an electric motor. The condenser is a heat exchanger that's located outside. It removes the heat energy from the refrigerant and essentially dumps those BTUs of heat energy outside the building. Often you'll see the condenser outside a house. The expansion valve, or the item that creates the pressure drop, comes in many different fashions, but essentially it's a refrigerant control valve. Some of them are electric and some of them are not. The thermostatic expansion valve, or TX valve, is probably the most commonly used in industry, and there is no electrical connection to it. This is its premise of operation. It's quite basic, where we have a high pressure warm refrigerant that has a plug at the end of it. Small tube with a plug. There's a spring which holds the plug in place, and the only way that this plug is slowly moved down is through a bellows. The bellows are controlled by a capillary tube and temperature sensor bulb. As this temperature of the refrigerant increases in temperature, the increase in temperature causes the fluid in this sensor to expand and pushes down through the capillary tube and pushes the bellows down. When the bellows is pushed down, it releases the valve slightly, and so some of that high pressure warm refrigerant is allowed to then empty into this large chamber and larger diameter pipe, which is a low pressure environment. When it does this, it is extremely cold, and that difference in pressure then is transferred back to the temperature sensor, where the gas or liquid inside constricts and shrinks a bit, and the bellows goes back to its original position, thereby closing that high pressure warm refrigerant outlet. It's an interesting self-regulated process. Finally, the evaporator. The evaporator is located inside the building, and it's either in an air handling unit, which would be inside a commercial or institutional environment in the ductwork like this, or it's installed over top of a furnace on top of where the regular heated air would come out. Instead, it goes through a secondary set of heat exchanger, which would then cool the air instead of heat it. And here's an example of this system in an institutional setting. The refrigerant is simply a gas that readily changes from gas to liquid and back again. There's hundreds of different types that operate at different pressures and different operational requirements for the size of the piping and the type of compressor used. One refrigerant is not used in every refrigeration or air conditioning system. So, to summarize, refrigerant is discarded and BTUs are dropped outside from the condenser. Whereas in the evaporator, the refrigerant is absorbing BTUs of heat energy from inside air. And that could be a house or a refrigerator or a cooler room. There are some additional components of AC units that we should be aware of as electricians, and those include things like crankcase heaters, filter dryers, receiver tanks, and sight glasses. Sight glass is simply something that is a visual indicator if liquid water were to get into the line. Although refrigerant may look clear and look like water, it is not. And when we look through the sight glass here, in the back, there is a moisture sensitive pad that if there is liquid water inside the refrigerant line, it will change color. A filter dryer is simply something that removes water moisture from the refrigerant and also filters out any particulate that may have accumulated through the operation of the compressor. And finally, sometimes there is a crankcase heater, which is essentially a small amount of heat trace or heat inducing wire that's wrapped around the compressor itself in cold environments to ensure that the oil in the bottom does not get too thick. Now, problems can arise if the refrigerant line becomes blocked because of pressure will rise until the line is ruptured. And if refrigerant leaks from the system, the compressor could be damaged. Now, if no air is blown past the evaporator, it will ice up. And these are all different types of issues that we can run into when we are troubleshooting or working with a cooling system. This is a split pipe from overpressurization, and on the right we can see an evaporator that is iced up because there was no airflow across it. Eventually it gets iced up so much that there's no way for air to even flow past it. And so we would have to wait for this to then thaw, and what a mess it is. The final portion we're going to look at is the control of the cooling system. Again, we're not looking at memorization of every single possible action, but instead a general understanding of what some of the different control parameters can be. Pressure switches are used in cooling systems often. We have a normally open on the low pressure side and a normally closed on the high pressure side. The normally open pressure switch will close once the system is filled with refrigerant, and it's almost like a safety device to ensure that we never run out of refrigerant. It should shut off the compressor. The high pressure switch is again a bit of a safety device because we don't want the lines to rupture due to a blockage. And so there is a maximum pressure rating that should not be exceeded, and it should shut down the compressor if we do get near it. Sometimes these pressure switches are contained in a single control unit with two separate pressure sensing connections. This is an adjustable on and off sometimes, 15 psi differential, which means it's going to turn on and off at different values or close and open. And we can see the differential sitting on the left. Differential meaning how many degrees do we need to have between the on and the off. This is a safety on-off, and we could set it at whatever PSI is appropriate for the system. Now with these pressure control sensors, there are two different ways that a thermostat can then control the cooling system. One of them would be for the thermostat to control the solenoid in a refrigerant line. The other one would be for the thermostat to control the compressor contactor. Let's take a look at the difference between these two forms of control. Solenoid control would have the thermostat control a refrigerant solenoid, and a solenoid simply controls the flow of refrigerant through the refrigerant lines. In this situation, what would happen is that the low pressure switch would determine when the compressor comes on and off. The refrigerant solenoid is in the refrigerant line and allows the flow through a cycle from the compressor through the evaporator to the condenser. What's a little bit more common is compressor relay control, and this is where the compressor cycles on and off with a relay, which is controlled by the thermostat and low and high PSI switches. Here's an example of yet another combination. This one is of a furnace, and we can see the low and the high pressure switch as well as the thermostat. The compressor itself is located here, and we have the indoor fan motor, which is going to blow that conditioned air throughout the home. This is yet another example of a control diagram where we have the high pressure and low pressure, a thermal protection switch, which is there to simply protect the compressor. Now notice that there is a secondary fan here. What is this one? Well, this is for the condenser. Remember, the condenser heat exchanger needs to have a fan that blows air across it, as well as the evaporator needs a fan to blow air across it. So there are two separate fans and also a compressor. This would be a fully fledged heat and AC system for a standard simplified version of control. We can see here the cooling thermostat, high pressure, low pressure, controls coil. And then we have here the heating thermostat with the high limit and the gas valve. There are two different speed settings here, and typically what we have for a single blower that would be providing either heat or AC is that it will turn at a slower speed or low speed when it's blowing warm air and a higher speed when we're blowing cold air. And this higher speed is to reduce the likelihood that we are going to ice up the evaporator. So what is required to install an AC unit in a house? Well, we've got our furnace, panel, and the outside is on the left. So we've got the condenser and the compressor, which are located outside, and there is also obviously a condenser fan. We have the evaporator, which is installed on top of the furnace. That's called an A-frame sometimes. Then we then have two refrigerant lines, which have to go in between the two different heat exchangers. And then we need a rather large connection, either number 8.2 or 8.3, depending on the size of the compressor, and a disconnect on the outside of the house. Finally, we need some form of a control wire, which will connect back to the furnace, and the furnace will then tell the condenser and the compressor when to turn on and when to turn off, based on our thermostat calling for heat or calling for cooling. Finally, heat pumps. A heat pump is very similar to what we have looked at previously in this presentation. The only difference is that a heat pump is able to take warm air out of the winter atmosphere and condense that heat and dump it inside the house. Whereas in summer, it works exactly the same as an air conditioner. Now, heat pumps have a definitive threshold of temperature that they can operate within, which means that a heat pump is really only useful in fairly temperate climates. Heat pumps are not able to remove heat out of air that is too cold. A -30 exterior winter atmosphere will have so little heat energy in the air that a heat pump would not be able to collect it and dump it inside the house. In this way, there needs to be some means of reversing the action, and that is taken by a reversing valve. This is not a mechanical valve, but more an automated system which determines the flow of the refrigerant based on the need of the building to have either heat inside or cool inside. Heat pumps are commonly seen in the form of mini split, which are just miniaturized heat pump systems where the condenser and the compressor are located outside and the evaporator is located inside. The reason they are so popular is because it is a relatively small footprint or renovation to install one into a building. All that's needed is one hole through the wall and the evaporator mounted on the inside.